Good morning, students. Today we are going to discuss the another relativistic equation, which is very important equation as far as quantum mechanics, quantum field theory are concerned. So this is about Dirac equation for a free particle, and thereby we are going to discuss Dirac matrices. So this equation is the second relativistic wave equation. The first equation yesterday we looked into was Klein-Gordon equation. So Klein-Gordon equation, in which this is a second order differential equation in both space and time coordinates. So both sides we have second order differential equations, and of course it worked out for the symmetry in space and time according to special theory of relativity. But on contrary, very important one is it couldn't explain the equations for the fermions. It could explain only for the bosons, that too for spinless particle, that too for spin is 0. So yesterday we were discussing about Klein-Gordon equation, and those equation it was explained only for the spinless particles for spin equal to 0. For example, k meson and pi meson, for those particles it will work out. And also very discrepancy was the explanation of negative energy. Negative energy states could not be explained by Klein-Gordon properly. So those discrepancies were removed by Paul Dirac. It's a very famous mathematician and physician. He was a very famous, next to Maxwell, Albert Einstein and Paul Dirac. So this is the hierarchy all physicists have used. So Paul Dirac was a very famous mathematician as well as physicist, especially theoretical physicist. And he introduced a new Hamiltonian, which is nothing but this Hamiltonian. So he explained boldly this. We are going to look into this equation maybe in a short time, and very famous equation. Okay, Paul Dirac introduced this Hamiltonian alternately of Klein-Gordon equation. Okay, so this is second equation in relativistic quantum mechanics. Paul Dirac, in fact, we can say that the whole universe is divided into two parts: radiation and light, bosons and fermions. So almost all the things can be divided into bosons and fermions, we know already. So if we were discussing about identical particles, in which we learnt about this factor, everything in the universe has been divided into two parts. One is boson and fermions. These words were introduced by Paul Dirac. One, and we know that Bose-Einstein statistics and Fermi-Dirac statistics we know already. So these two quantum statistics which will explain all the matter and the radiation, so we know already. So wherever or whenever he goes for a conference, if at all if he wants to mention these two statistics, he would say Bose statistics, Fermi statistics. Rather, everyone will say Bose-Einstein statistics, but he would always say the Bose statistics, Fermi statistics. And we know that the fine structure constant, we have already studied fine structure constant in hydrogen atom. In fact, fine structure constant can be used in atomic physics also. In spectral techniques it has been used. Alpha equals 1 divided by 137, fine structure constant. This was introduced by him. And very famous introduction of matrix mechanics, nothing but Ket-Brown notation. So it was introduced by Paul Dirac, Ket-Brown notation. And Dirac delta function, very famous one. Without Dirac delta function we can't move any mathematical steps in quantum mechanics. So that was introduced by Paul Dirac, Dirac delta function. In fact, in 1930 he wrote a very famous book, Principles of Quantum Mechanics. Actually most influenceable textbook in the world in quantum mechanics, Principles of quantum mechanics, in which he introduced all the things which whatever I mentioned. In addition to that, we know that in the year 1925, Werner Heisenberg introduced matrix mechanics, and in 1926, Schrödinger introduced wave mechanics in the year 1926. So there were two avenues of attack in quantum mechanics. So one was about matrix mechanics, then another one was about wave mechanics. In the year 1927, Schrödinger himself proved that both the mechanics are equivalent. But in the subsequent years, Paul Dirac wrote a very, very famous book in which he mentioned these two mechanics, and he mentioned about the quantum mechanical system in which both the systems can be represented in the same way. That is, the quantum mechanical system can be represented in terms of matrix mechanics as well wave mechanics in the same way. Both are equivalent. So this textbook, Principles of Quantum Mechanics, in the year 1930, it was very, very famous, written by Paul Dirac. Very, very famous. And most the influential book in physics. And then onwards, lot of books have been erased. So Paul Dirac, he was born in the year 1902 in Bristol, England. His father was Charles Dirac, and they were the immigrants from Switzerland. Their ancestors were from France. So his father knew about French very well. So he went to England, and in fact he was a teacher for a French class. So he was a French teacher, because as he said, his ancestors were from France. So he knew very well. And he married, daddy married a librarian in Bristol. In Bristol town there was a library, and he married a librarian. So educated family. So if it is educated family, automatically the children have to learn, no other way. His siblings were his elder brother and younger sister. So 3 children were there for his daddy, for their parents. So elder brother and Paul Dirac and younger sister. And daddy was very, very strict. Very, very strict in the sense, in the school days, he used to say that he would everyone should talk to him only in French, not in English. Of course, when he joined the school, the local communication, local language would be only in English. So he knew very well. Dirac knew very well about English, how to communicate with all of us. But his daddy says that if you want to talk to me, you have to talk only in French. But he was very difficult in talking French. He found it very difficult. So at the end, he stopped talking to his daddy. It continued in the school also. So continued in the school in the sense, in the school also he would never talk to anybody else. He had no friends at all. He would always concentrate only on mathematics and physics. He was well versed in mathematics. And he would never have any communication with others. He would say, somebody asked some questions, immediately he would say yes or no, that's all. So in the school as well in the house also, he would practice that. He would say only yes or no. So it continued. He finished his schooling in the local schools in Bristol. Then after that, University of Bristol, he had his undergraduation in engineering. Because in the schooling, usually they will have some modeling. Like for example, modeling in the sense, it always connected with some engineering. So like modeling, electroplating, molding. So these are some models usually they will keep in the schools. So he was so inspired with seeing those models, and immediately he took engineering subjects. So he graduated engineering in the University of Bristol, England, in the year 1921. In 1919 there was a war. Okay, 1919, First World War started. So he finished his graduate in the year 1921. So this is post-war depression. So surely he would not have obtained any job. He did not obtain any job. So he searched for another degree because he was so curious to study. So he searched for another degree. So he could obtain one scholarship from BA Mathematics. So at that time people used to say BA Mathematics. Nowadays only BSc Mathematics. Those days we will say only BA Mathematics. So he could obtain the scholarship for BA Mathematics. He started doing BA Mathematics and he joined second year because already he won the degree, engineering degree. So he was exempted to do first year. So he joined second year, directly second year. So in the year 1923 he finished that graduation also. So he had engineering degree as well mathematics degree. So in the year 1923, so at the time Einstein was very famous. So in the year 1922 Einstein got Nobel Prize, and all the universities in and around the world, they used to call Einstein for some talks, for discussion, for giving some lectures. So one such talk was taken by Albert Einstein. He could attend that lecture. So he was so inspired about Einstein's speech on special theory of relativity, especially. So general theory of relativity. Because he knew very well about mathematics. He was well versed in mathematics. So he started learning special theory of relativity. So he was so attracted in the sense, he took his PhD in physics. See, just look over here. He had 3 degrees: engineering, mathematics, and PhD in physics. Under great scientist Fowler. He was a very famous man, Fowler, from Cambridge University of Cambridge. So in the year 1926, he finished his PhD. He was the first student in Cambridge University who did his PhD on quantum mechanics. So first student. So in the year 1926, he completed his degree. Then after that, he had some collaboration with Niels Bohr. He went to Copenhagen, Niels Bohr, Denmark. Then he was doing some works on quantum mechanics, especially on theory of relativity. So in the year 1927, very interesting one was 1927. There was a Solvay conference in which all the scientists will usually gather together, and they would present their papers on recent invention. So at the time, one of the presentation was made by Klein Garden. So Klein Garden, both the scientists, they presented the paper on Klein Garden equation in particular on a particular day. He joined that conversation. Then after that there was a break. So 10 minutes break there will be usually. So between some talks. So when he was sitting on the somewhere, Niels Bohr came and approached him. And of course they were friends earlier. And Niels Bohr asked him, "What are you doing, Paul Dirac? And what is your research work now?" And immediately Paul Dirac said, "I am doing research work on the quantum mechanics with special relativity. So I am going to expose the results of special relativity. I am going to take this equation and I am going to implement in quantum mechanics." And Niels Bohr immediately told him that just now we heard the talk from Klein Garden. They have finished already the equation about relativistic quantum mechanics. But Dirac replied immediately that I am not satisfied with the equation because this will work out only for the bosons, especially for spinless particles. But I would like to find out the new relativistic equation which connects for the fermions, for all the spin particles, for half integer particles. Then after that conversation went on. So as I said earlier, in 1930 he wrote a very famous book, and also he explained about antimatter. He predicted the antimatter. Explanation of negative states of energy. But we know that in the year 1932, Anderson he he found out the antimatter, antiparticle, especially positron, while doing the experiment on cosmic rays in the presence of magnetic field, for which he got Nobel Prize in the year 1936. But Paul Dirac, earlier he got the Nobel Prize in the year 1933, and he shared the Nobel Prize with Schrödinger. So Schrödinger shared the Nobel Prize with Dirac in the year 1933. For 32's Nobel Prize was given to Werner Heisenberg. So all the three in the year 1933. So in the year 1933, 3 persons got Nobel Prize: Werner Heisenberg, Paul Dirac, and Schrödinger. He was so interested in writing books. So he wrote many books. Out of many books, we can say that Principles of Quantum Mechanics is very, very famous and influential book. Then Spin-offs of Gilbert Space, he wrote that book, also very, very famous. Lectures on quantum mechanics and lectures on quantum mechanics and relativity. And already in the year 1905 and 1915, Einstein wrote the very, very famous 2 books about relativity. We know it. But in 1970s, he wrote a very, very famous book, Special of Relativity, which contained only 70 pages. So in a short null, how to explain special of relativity. He worked as a mathematics professor in University of Cambridge for a longer time, more than 20-25 years. Then after that, he went to US, to Florida and Miami University. He worked as physics professor. So very, very famous mathematician as far as all physicists are concerned. Next to Maxwell, Albert Einstein, and Paul Dirac. So Paul Dirac was a very, very famous mathematician. Okay. So we will look into the Paul Dirac's equation, which is the second relativistic equation. The first equation yesterday we were looking at Klein-Gordon equation, okay, which could not explain for the whole spin for the fermions. And today we are going to discuss the Dirac equation for a free particle, and thereby we are going to get the ideas about Dirac matrices. Okay, so this is just the portrait of Paul Dirac, 1902 to 1984. Okay, so we are going to continue with yesterday's discussion. So yesterday we started with the non-relativistic equation, and we discussed about especially symmetry in space and time. Okay, so which we are going to consider as invariance in Lorentz space. So symmetry and the symmetry of space and time coordinate and under Lorentz transformation. It has to work out in all the frames of reference. And we were discussing about how Klein and Gordon, Schrödinger himself introduced the specialty of relativity results into quantum mechanics, his own results. You know, space and time coordinates were not matched in non-relativistic equation. Schrödinger equation, space and time. We have partial d squared psi by dx squared on one side, and we have partial d psi by dt on the other side. One is second order differential equation, another one is first order differential equation in time. Both could not match out. The symmetry of space and time could not work out here. Okay, so Lorentz invariance will not work out here. So that's why they modified. They introduced this equation into quantum mechanics. They could obtain second order differential equation in space and second order differential equation in time. So now this one symmetry exists. Symmetry between space and time will work out. But Paul Dirac thought on the other way around. He used this equation, Hsi equal to Esi, the eigenvalue equation of Schrödinger. Very simple equation. And we know the operator for E can be written as I cross d psi by dt. In Klein-Gordon equation, we know that the space and time both matched, but in second order differential equation, he thought on the other way around, why can't we match with the first order differential equation? So that's the idea. Because right hand side we have I cross d psi by dt. Okay, and left hand side also it should match with d psi by dx. Okay, it's a beautiful conclusion. See, you have right hand side single order differential equation with respect to time, and left hand side also he guessed that it should be in terms of single order differential equation in terms of space. So he guessed and he predicted this Hamiltonian H equals c times alpha dot p plus beta mc squared. So very boldly he wrote this equation. It's a very very famous equation. He guessed all the things, he predicted, and at the end he could arrive this equation. And there is no derivation at all for this equation. He predicted this equation. The Hamiltonian is c times alpha dot p. We are going to introduce what is alpha and beta later. So c times alpha dot p plus beta mc squared. We know this quantity very well, momentum operator, and we know mass of the particle, c is velocity, we know already. What are this alpha and beta? This is a vector operator, this is a scalar operator. Look at the right side equation, you have mc squared. So those are all values. Okay, so beta must be a scalar operator. So we can conclude immediately beta must be a scalar operator, it should not be a vector operator. But alpha dot p is a momentum operator. Okay, alpha, first thing is alpha will not be a number. Okay, first point, alpha should not be a number. Alpha is independent of position and time. Okay, alpha is not connected with momentum. So three things you have to remember. Alpha is not connected with momentum, first point. Second point is alpha is not a number, and third one is alpha is independent of position and time. Okay, but what is alpha? As I said, alpha is a vector quantity. As I said, alpha is a vector quantity. So he guessed in such a way that alpha must be a matrix. Alpha must be a matrix. He guessed. You know, this guess came from this equation. E squared equals c squared p squared plus m squared c to the power 4. Suppose we want to square the term, perfect square. We want to have a perfect square of this equation. How to have a perfect square of this equation? That is cp plus mc squared whole squared. I can make a perfect square of this equation like a plus b whole squared. So he guessed in such a way that he wants to have a perfect square of this equation. Okay, a plus b whole squared. If it is a plus b whole squared, so we know that a and b are operators. So we can say that a squared plus b squared plus ab plus ba. If we want to make a perfect square, a plus b whole squared equals a squared plus b squared, the remaining term should be 0. That is ab plus ba should be equal to 0. Only then we can have a perfect square. Correct? Just listen to me. You have this equation, e squared equals c squared p squared plus m squared c power 4. Okay. If we want to have a perfect square, this must be cp plus mc squared whole squared. There should not be any remaining terms. So similarly, a plus b whole squared equals a squared plus b squared. The remaining term ab plus ba must be equal to 0. So that's a conclusion we can have. Suppose if a plus ba equals 0, and a and b must be anti-commute with each other. Correct? Anti-commute with each other. If ab equals ba, they will commute. If ab equals minus ba, they will anti-commute with each other. A and b are anti-commuters. What are the numbers? As I said first time, as I said, alpha will not be a number. Numbers will commute with each other. 4 multiplied by 5, which is equal to 5 multiplied by 4. So numbers will commute with each other. So alpha will never be a number. First point. Alpha is independent of p. Alpha is independent of space and time. So three things you have to remember, as I said. And alpha must be anti-commuters. So alpha will have a property of anti-commuting property. Okay, as I said, alpha dot p. So it can be alpha x in terms of components. Px, py, pz. Here it is alpha x, alpha y, alpha z. So you will have alpha dot p will be alpha x, px plus alpha y, py plus alpha z p z. So there will be three components of alpha, which is nothing but Pauli's matrices. All Pauli's matrices are anticommuters. That's a beautiful idea. All Pauli's matrices are anticommuters. Pauli's matrices, they represent spin matrices. Alpha x, alpha y and alpha z. Easy to remember. Alpha z is easy to remember. It's 2 by 2 matrix. So all Pauli's matrices are 2 by 2 matrix. When you are going to finish 2 by 2 matrix, the next one will be 4 by 4 matrix. Okay, they will not have any 3 dimension. So now coming to the point, as I said, alpha x px plus alpha y py plus alpha z pz. How to remember easily alpha z? Alpha z is nothing but one of the z component of Pauli matrices. It is nothing but 1 0 0 minus 1. Easy to remember. 1 0 0 minus 1. 1 stands for positive x direction or positive z direction, and minus 1 stands for negative z direction. Okay, one is for spin up, another one is spin down. So easy to remember. Alpha z equals 1 0 0 minus 1. Okay, so he concluded that alpha must be Pauli's matrices. Alpha x, alpha y, alpha z, they are all Pauli's matrices. So as I said, alpha is an vector operator, beta is nothing but your scalar operator. Okay, so with this introduction, we are going to look in detail about the second relativistic quantum mechanics, which is nothing but Dirac equation. So in the previous section, we discussed Schrödinger relativistic equation, which is in Lorentz invariance form. Of course, Klein-Gordon equations were surely in accordance with the Lorentz invariant form. Okay, because symmetry in both space and time. Both the sides we have same order, second order differential equations in space and in time. When the wave equation is in the first order in time, it must be first order in space coordinate, he guessed. So Paul Dirac guessed and he used the eigenvalue equation. Klein-Gordon equation does not fully explain the negative energy states, and it can only apply for the spin zero system. So we know already. The occurrence of negative probability density can be interpreted as the electrical charge density. Yesterday we discussed in terms of charge density EP. Can you remember? This is your EP. Hence it can be positive as well as negative. The theory is useful only for a system of particles having both the signs of charges. Okay, that probability density, yesterday we were discussing about the system contains both the charges, it will work out. So this is what yesterday we discussed. These discrepancies of Klein-Gordon equations can be eliminated using Dirac's theory. So we are going to introduce now. Dirac was influenced by Maxwell's equation. So we know that Maxwell's equation, out of 4 Maxwell's equations, 2 Maxwell's equations are differential equations of the first order. So they are symmetry in both in space and time. So which are the first order equations in both space and time coordinates. The equation is linear in d by dt, and on account of symmetry it should be linear in px, py, pz. So Dirac modified the Hamiltonian in such a way as to make it linear in the space derivatives. Okay, Dirac used the wave function which is invariant under the Lorentz transformation. Here too we have a negative energy states. So in the equation here also we have a negative energy states, but after 2 years he could explain clearly about the negative energy states, what he predicted as antimatter, antiparticles. For every particle there will be an antiparticle with a negative sign. For example, if you have an electron, the antiparticle will be your positron, which will have the charge of plus E, that is minus E and plus E. So they will annihilate and they will have pair production with there. So they will have electron and positron, again they will join together and with the production of energy.